Good morning, everyone. We will continue chapter 5. Chapter 5, last meeting we have discussed about how you can establish, how you can build a shear force diagram and bending moment diagram. Just to give a quick review, when you have a beam and you apply a transverse force like this way, it means that inside the beam there are two internal forces are generated. One is the shear force Phi, another one is the internal bending force M, V and M. Okay. The purpose of us doing SFD and BMD is to find the highest or the maximum shear force location and the maximum bending moment location. Because by knowing that, we know that is the particular location that the beam may fail. And therefore, we would like to quantify the stress. The Phi will give you shear stress. The M will give you normal stress. We haven't reached yet to how you determine the shear stress from Phi. Last meeting, we discussed about how you can determine normal stress from bending moment. The equation is sigma equal to MC over I. Okay, good. Now, in our previous meeting, I have demonstrated to you how you derive the SFD and BMD by performing section method, one by one. This was what we did in last meeting. We do it before and after the applied load. What you should remember is the convention of Phi and M. If you do the sectioning by, you do the sectioning from the left to the right, be careful, the Phi is going downward, the M is counterclockwise. That's the positive convention. And then you can do a equilibrium analysis, sigma Fy equal to 0, sigma M equal to 0, to get the value of V and M before and after the applied load. You may define like 6 position because you have 1, 2, 3, 4 applied and reaction forces. By knowing the Phi and M before and after the applied force, V1, M1, V2, M2, this is before and after, sorry, V2 and V3, yeah? Before this 46 kilonewton, then you can draw the SFD as well as the BMD from the value you calculated. Okay, now I would like to go with the mathematical point of view of how the SFD and BMD are intercorrelated. So pay attention. Suppose you have a beam AB supported by simply supported fixture, simply supported beam like this one. This is beam, this is roller. That is how we describe as simply supported beam. It is applied by a distributed load of W. It is not even a concentrated load, it is the whole system is applied. And then we do a partition analysis. This is the element of CC prime. Look at this, this is the zoom out, the zoom in of CC prime particular element. Look at this one. When you see from the right hand side, the Phi is going downward, the M is counterclockwise. When you see the element from the left hand side, you'll see V is upward, M is clockwise. Both are positive convention. Okay? Now from here, we apply an equilibrium equation for sigma Fy equal to 0. Sigma Fy equal to 0, evaluate all forces in Y direction. So let's start from the left. What you find is Phi. Is Phi positive or negative? Positive. So you put Phi positive. And then you have this another Phi with distance delta x. Of course, there's a difference between Phi and the new Phi, or we call the Phi prime. The difference is delta Phi. Whatever the value is, it may be different. Therefore, we apply this delta Phi Because this is upward and this is downward, we put a minus. V plus delta V. This is the sigma Fy. What is remaining is the force from the distributed load, the W itself. If you know the equation of the W, the distributed load, we may then just multiply it with the function x. So this is the total distributed load in this particular location. W times delta x. That this dashed line represents the total of this distributed load applied in the middle. Okay? Therefore, it will also add another force going downward, W delta x. V and V cancelling each other, therefore you get only delta V. Delta V is equal to this minus delta V minus W delta x equal to 0, therefore you get delta V is equal to minus W delta x. If, listen to me, if the V is replaced by y-axis and the x is the x-axis, that delta V equal to minus W delta x is a linear equation with W as the gradient. It is just the same as you try to extract the elastic modulus from your stress strain curve. Delta sigma over delta epsilon, right? Then you get E as the Young's modulus. So when you look at this, we can interpret that if you know the applied load, that applied load becomes the gradient of your shear force diagram. Like what you did in stress strain curve. If you know the elastic modulus of your material, it becomes the gradient of your stress strain curve. Agree or not? Similar. So when you can define the applied load of your beam, it will be the gradient of your shear force diagram. Therefore, if you want to get the gradient, you can get delta V, dV over dx is equal to minus W, because W is going downward. Yeah? And then, meaning that when you want to get the delta of delta V, it is actually the area under the curve of C and D. We'll finish this first, then I will demonstrate. So we have done with the sigma Fy equal to 0. We found that the applied load is the gradient of the SFD. And then we continue with the sigma M equal to 0. In sigma M equal to 0, you can get back to this diagram of elements. You'll find that this is M, moment is clockwise. Therefore, clockwise is minus 3. This is counterclockwise. M plus delta M as the this difference. They have delta M. It is positive. And then what else? The V. The V has, it is doing the sigma M C at C prime, yeah? At C prime here. So V has a distance of delta X to C prime. Therefore, the moment because of V is V times delta X. This one. From C prime, V is creating a clockwise. Therefore, V times delta X is minus. Yeah. And then what is remaining is the dashed line, the W. The W delta X, W delta X going downward, making from C prime, making a counterclockwise movement, and it has a distance of half delta X to C prime. Therefore, you can get this plus moment. You combine everything, you can get this Delta M is equal to V delta X minus half W delta X squared.
What is W delta X?
W is the applied load, and delta X is the element that we are now analyzing. So W delta X represents the total force. Okay, you add up every force applied along this line. So it is literally the total force along this delta X. Okay. Now you have this equation there. That's a parabolic equation. If I then assume that the delta X is very small, therefore delta X squared becomes very small, even much smaller. Okay? By that assumption, this part is negligible. In short, delta M is equal to V delta X. Without this, that's how we derive the relationship between bending moment V and X. And you see again, similar to that part, delta M times V equal to V delta X. Without this, it is again a linear equation, and V becomes the slope. So in short, what you need to realize, when you apply a transverse force to your beam, the applied force becomes the gradient of your SFD. After you derive the SFD, the shear force itself becomes the gradient of your BMD. That's how it is intercorrelated in each other. Okay? Now, what's the benefit of doing this? Let's get back to okay. Let's go from here. Yeah. Yeah.
What we analyze is from C until C prime. Why the integral is from C until D point?
The integral from C
Until point D.
point D.
But what we analyze is the C.
Suppose you, by this equation, you can always use this equation to find the difference in moment, any location inside the beam. So this is becoming your governing equation. Okay? Delta M delta X equal to V. So if you would like to know what would be the difference in moment between A or D, C to D, C prime to B, you know that it is just you integrating from the starting point to the end point. Okay?
Thank you, sir.
Yeah. Now look at here. Applied load is the gradient of the SFD. The SFD itself is the gradient of the BMD. Okay? So, you see now the beam is under concentrated load of 20 kN, 46 kN, 40 and 14. Okay? Now, the 20 kN, if I ask you, is it a constant or a function? Constant at this particular location. Then after A, nothing. Okay? If you integrate something from nothing, what will appear? Constant. So when you have a concentrated load, you want to know the shear force generated by it. It is a constant. As I told you in here, yeah, integration. A concentrated load has no function. It's just applied, and after this nothing. So meaning that from that point going onward, no applied load. Because no applied load, if you integrate, what you will get is a constant. Okay? So if you look at this one, the constant itself is determined by the 20 kN itself. So the 20 kN becomes the constant itself. KU1. There's no gradient though. The gradient is nothing. So no gradient, constant. No changing. 20 is 20 kN. It is going downward, therefore it is minus. Okay? Until it reaches the second applied load, 46 kN. Again, 46 kilonewton is a constant load. And then, a concentrated load. And then no load applied after that. Therefore, no gradient. Gradient is constant again. Because this is minus 20. Add up by 46, you are subtracting the 46 minus 20, you get plus 20, 26. And then constant gradient. Another 40 kilonewton going downward, so 26 plus it is 40, it is minus going downward. So 26 minus 40, you get 14 minus 14. And then from 14, no gradient. Reaching D, you find the final force that will make the system in equilibrium, which cancel the 14 minus, add up by the 14 positive. So start from 0 and in 0. So that's how the applied load, the transverse applied load, is converted into a shear force diagram. It is pretty easy now without you bothering doing the sectioning one by one, because now you know that, well, if I know it is a concentrated load, there's then no gradient. So I just apply 20 kilonewton downward because it is minus constant. You follow the direction of the applied load. Continue to how you derive the BMD. Again, the SFD is the gradient on the BMD. Different with this, when the applied load has there's no applied load in the real one, but for the SFD you find that the V becomes constant. When you have a constant value, you integrate it toward X, what will you get?
X.
Constant of X. Constant of X, because it becomes the gradient. Yeah. So now this 20 kilonewton becomes the gradient of the BMD, the slope. It is minus 20 kilonewton, so it is going downward 20 kilonewton, and it is multiplied by the X. Yeah, by the X. So it is going downward. Because the distance is 2.5. 2.5 times 20 is 50. Is 50. Okay? Okay. Yeah. Section in the middle between 20 and 46, because you want to get the equation. Okay? kilonewton, and then this is the V and this is the M. You put this section with a distance of X. Let's say it has a distance of X from here. So it has an X distance. Okay? This is the M. Okay. If it is a concentrated load, the V becomes the applied load itself. Therefore, it does constant. Going downward, and it is minus 20, this is minus 20 kilonewton. Now comes to M. M is the applied load multiplied by the distance, right? So it is counterclockwise positive. This is 20 kilonewton making also positive. 20 kilonewton times X equal to 0. Therefore, M is equal to minus 20X. This is the equation. When you put X equal to 0, M is 0. When you put X equal to 2.5, M is minus 50 kilonewton meter. So that's how it is proven that 20 is actually the gradient. Okay, continue, yeah? Continue. continue. I want you really to understand the concept of this internal force. Okay. Now let me continue with the next section. In between we apply sectioning. Another between we apply sectioning because we believe there will be a changing. Right? What will you do? You know that there is a 20 kilonewton applied here. This is 20. And then 46 kilonewton. Okay. And then Phi is applied. M is the internal bending moment. And it has a distance of x. The distance between 20 to 46 is 2.5 ya? Benar nggak? 2.5. Okay. Now guide me. Sigma f y equal to 0 will give you phi negative minus 20 plus 46 equal to 0. Therefore phi is equal to 26 kilonewton.
Yeah.
Okay.
Yeah.
Look, it is positive now.
Yeah.
The V becomes positive. Okay, now M. Sigma M equal to 0 at this point. Okay? Guide me. M is positive, negative? Positive, good. Now look at 20. How should I deal with 20? Positive or negative?
Positive.
Positive, good. So it is 20 times X. Okay, then we should deal with 46. What should we do? Minus 46 times x minus 2.5 equal to 0. This will lead you having 20 minus 46 minus. Sorry. Let's do it. Let's do it together, step by step. Let me jump over here, okay? Now, let's solve this equation. M by 20x minus 46x. Okay, let's do it because someone has maybe wondering, yeah? 20x minus 46x minus times minus becomes positive. So it is positive. 46 times 22.5 berapa?
115.
115 equal to 0. Begitu ya? Agree ya? Coba dicek lagi benar ya? 46 times 2.5. Benar ya? Oke. Okay. Now I want this equation to becomes M equal to something. Therefore I will write M. Ini dulu ya, ini kelar dulu nih. This is becomes minus ya?
Yeah.
Minus 26x plus 115 equal to 0. Therefore M is equal to 26x minus 115. Okay, check ya. Check. When x is equal to 2.5, M becomes, when x is equal to 2.5, M becomes
50.
Hitung sendiri, hitung. Oke, hitung dulu.
50. Yeah, minus 50.
Minus 50 ya?
Yes.
Minus 50.
50.
That's it. When the x is 2.5, M is minus 50. Agree or not? Okay. Now when x is equal to, what is the farthest I can go before 40? It is 5.5, yeah? Because 2.5 plus 3. So I would like to know, I want you to calculate if the x is equal to 5.5, what would be the M? Jalan aja kalkulasi, ayo.
28.
Calculate.
28.
Calculate dulu. Please calculate, try calculate. Michael, I do it into my head. I don't believe you. Oh, you did. Okay, good. You did. Arya Satya. Cannot. You should do it with your finger.
258.
28.
See. 200 or 28?
28. 150 minus 150.
5.5.
5.5.
Yeah, 26 times 5.5 minus 150.
28.
28.
28, sir.
So, now my question to Brian then. Brian, is it allowed for me to use this equation if the x is between 0 to 2.5? If you put 0, x equal to 0, what you will get?
Minus
Minus
115.
115. So, this is only applicable in this particular section. Because that's the location you derive it. Therefore, every partition has its own equation of BMD, bending moment diagram. For the first partition, that was the equation. The second partition, this is the equation. And you also can do it for the third partition, which is here.
Yeah.
That's how the math, and this is how you physically do it. This is how you check. Arya Satya, this is how you check whether your answer is correct or not. Look, this is minus 20 kilonewton when it is x equal to 0, no moment of course. When it is moving with respect to the x, 2.5, so 20 kilonewtons times the 2.5. Okay, it is minus 40 kilonewton, meaning you are calculating the area under the curve. Okay, now you would like to know what would be the moment because of the 26 kilonewton. Just easy. 26 kilonewton multiplied by 3. 78. You have 50, but this is minus 50. You have positive 78. 78 minus 50, you get 28. Sir, aku suka yang itu. Boleh. If you like to do it very carefully with the derivation, yes, you can. But this is also a physics phenomenon. You can. This is minus. Yes, the bending moment is minus. This is positive. Bending moment positive. So 26 times 3 is 78. Positive minus plus 78. 20 become 28. Again, this is minus or positive? Jarvis. Minus. What is the bending moment because of the 14 kilonewton?
2.
Huh? 20. Minus 28.
Minus 20. Minus 28. You have minus 28.
Plus
0.
Minus. Yes. 15. 14 is minus. Right? This is minus. Ini minus, positive, minus. So 28 positive minus 28 becomes negative. Negative becomes 0.
So, sir, on the test, we don't need to derive the equation.
I have done my part. It is then your part to choose which move you like.
if we
Whether you do it a very manual way of one by one, like before and after, or you do what like I demonstrated by the sectioning in between, or you can just watch and calculate by a simple algebra. Since Johan like this one more. Wait until you see the SFD is in its function. Okay, let's go with this now. Let's go with this now. The beam has 3 applied forces of 90, 40, and 54 kilonewton, and a distributed one. And Johan may get tricked with this. The 20 kilonewton per meter is the applied load. That's the gradient and the constant of the applied load. 20 kilonewton per meter. Gradient ya, itu ya. So, okay. If you find this, the first step you do is what? Attention. Sigma FD. What? Wrong. FBD. Come on. FBD is must. You make FBD to solve what? The reaction forces at A and B. Apparently, the slides demonstrate is you first determine the reaction force at D, not A. Therefore, because you are interested at D, You do a sigma moment at A. If you want.
Get the.
Okay? Watch. When you put sigma MA, you're not inserted anymore with AY and DX because it is exactly at the location, right? So you are interested with stack 90, 54, and D, and this one. So it was that was question, right? Whose question was that? How should you deal with the distributed load? It's you, Rafi. Yeah. So when you do the FDD analysis, you want to simplify that distributed load becomes one's representative load. So what you need to do is, because you know that it is 22 kilonewton per meter, you multiply it with the
length
of 2.4. 22 times 22 kilonewton meter times 2.4 meter, you get 52.8 kilonewton.
Okay.
And it is applied exactly in the middle with a dash line because it is imaginary. Because you are trying to to replace this distributed load with a single load, but in reality the single load does not exist. Now you do it from 90 kilonewton. 90 kilonewton is clockwise or counterclockwise from A? Clockwise. So it's minus, yeah. Minus 90 times 1.8. Good. Then next 50
minus
54 minus 54
times 4.2.
Berapa?
4.2.
Good. Then
Minus lagi.
Minus.
Ya minus lagi.
Plus.
minus lagi.
Plus.
Plus.
Oh, plus dulu. Oke, boleh. Plus
D.
FD. Oh, RD deh.
Ya.
RD
Times 7.2.
Then the last one.
Minus
52.8.
52.8.
52.8. 52.8.
8.4 times 8.4. Yeah.
Oh, no, not yet. F-nya apa?
Kita cari
Dari reaction to
Yes, equal to 0 ya?
Yeah.
Equal to 0. So you can get RT easily, because everything is known.
Yeah.
The D is 115.6 going upward, so it is good. So it is. You know that this is a constant load. Sorry, a constant slope. Because it is a constant slope, and minus it's going downward. Okay. Now we will continue. We continue constructing the BMD. Okay, the BMD. From this one, let me ask you, what sign for the bending moment for this one? Negative or positive? Positive, negative, positive. Okay, good. Yeah. What is the bending moment because of that? Because of this partition. At B, what would be the bending moment at B? Before 81.2 times 1.8. That becomes the bending moment at B.
Yeah.
And then this is ini loh hasilnya nih 146.2. Yeah? Wait. It's my wife. I can control from it. Okay. Now this one.
Yeah.
It is a negative one. So the bending moment you can imagine now before you look at your BMD directly, you know that it is positive and constant slope. So it will go up. Stop until 146.2. Okay? And then after that it should go down because there's a minus 21.1. So 146.2 minus 21.1, you will get 125.1. Going downward. Another going downward. So the BMD will be look like 146 minus 21.1 going downward, another 188.4 going downward, and then this one is the most difficult one because it is a linear equation. When you integrate once, it becomes parabolic. When the slope of a parabolic is negative, it creates this shape, not this shape. What I'm talking here is When you write the BMD is this way, it is wrong.
Okay, how do we know?
There is only for negative, yes. If it is negative.
If the slope is negative, right? Slope is going downward because then it is negative.
But if it's
A negative has a ini.
Oh yeah.
That's the parabolic when it has a negative
yeah.
slope, and when it has positive, it is this one. So we draw this BFD, this shape, because we know that the gradient is slope. The slope is going downward.
So the first area would be 146,2x.
The area below the curve of SFD, the total is 146.2. This will be the bending moment at B.
Yeah.
Well, main function is 146,2x.
Bukan, the function is 81.2 times x.
Oh.
The moments are
Distance.
I see.
Because 146.2 is the area of, or the result of you multiplying 81.2 times distance, which is the bending moment itself. Right?
Yeah.
So if you're standing at B, you look at 81.2. 81.2 have a distance of
1.8.
1.8. Therefore, the bending moment generated at B because of this number is this one.
Kalau dicek lagi, apa lagi sih setiap itu?
If you need, if there's a need or there's a question for you, determine the equation of BMD for every chord. You have the option but to do the section I just demonstrated now.
If we have.
What is the equation for this BMD? Itu kan gitu kan? Define the equation of BMD of between D and E. Meaning you have to find the equation of this. What is the equation of this SFD, and you integrate once.
But we can do the section in from right.
Exactly.
Kita nggak bisa ngambil dari shear force, shear itu ya. Dari slope-nya terus saya balik.
This one.
Iya. Dari slope.
In order to get the equation, cannot. Because it will be in a function of x, but the x is defined from here. If the x0 is from here, you can.
Jadi integral bisa. Kayak integral yang ada lower bound and upper bound.
As long as you can define this equation, yes.
Susah.
So you need to define this equation first, then integrate. Meaning that you don't need to go with the m here, you go with this. Find the equation of this linear equation, and then integrate once. And when you need to find the value, you integrate from B to E. Okay, I think we stop here first. We stop here by now. We have done chapter 5. Yeah.
Oh, so fast.
Fast. Chapter 5 done.